It's my honor to appreciate the organizer, and she and his colleagues make this wonderful workshop. And it's my honor to speak for my group. And in the past 30 years, when I was in Stony Brook, I bring some people in this list, and they did the work. I just summarize to say what I've done. I believe to me, I answer to everybody. 30 years, I did go in lots of circles. Now I recognize that I have a new direction to go. Don't go back. Okay, here's my summary. Machine intelligence, including machine learning, they should be priority driven, not the data driven. Then go. Which way go down? Next slide. We can move this one.
Yeah, that's the one. Hit escape.
Yeah.
Okay, skip. Okay, I keep talking.
You keep talking.
Those people I think over 30 years. Some older ones, on day one, I was in Stony Brook. And so they're still helping me in different regard. They provide their results, they provide their idea, then I summarize, then get back to them, what am I thinking? So they'll help each other make this talk here.
I just use the left button.
Okay. The talk is very simple, just 4 categories. Go back. No, go back. Yeah, I go very slow in the first few slides. After that one is not important. LdCT is the energy goes through the body. The body is the black box. If energy pass the body, come out, nothing interact in body, we get a piece of paper, nothing there. So we look for contrast. Contrast that comes from energy interact with tissues. We only have that contrast. Reconstruction brings you the contrast. From contrast, you can recognize where the border is. The contrast is dynamic, it's not intensity. Dynamic contrast. From one voxel to next voxel is a tissue property reflect this contrast. Okay, now we have different way to get a contrast. I will talk about the photon energies for CT. That's only bring contrast. So we have people come here to my laboratory teaching me what this virtual image come from. Work with physics. So if we inject in the iodine for do spectral and photon counting, you have 2 material, inject material or soft tissues. When you compute the VMI, you forget about iodines. You're only looking for tissue images. If you ignore the engine and the iodine, you have bone as a reference. They're bone soft tissues. For the problem I have interest now, long nodule, corn polyps. There's no bone involved. So you have 2 material from counting or from 2 spectral, you only use tissue component. Right? Okay, let's go next one. So you move. Oh, let's go to before it goes to the dual spectral, let's go to photon counting. Photon counting does the same thing. You make a very under windows. You compute the images. You compute the VMI. I emphasize the VMI because we can compute the image for each KV. Each KV bring different contrast. That's what I need. You use dual spectrum, triple spectrum, photon counting. The goal is to give you contrast. Go through VMI. So for the photon counting, you can do the same thing to give VMIs. In the last line, load, from those modalities, dual spectrum, triple spectrum photon counting, you end up soft tissue, then compute the VMI on the soft tissues. If you put the bone inside, it's okay, naturally expand. Now come to by single spectrum. This is the trick. Some reviewers say that Jerome, physics is a physics plus image processing. Say Jerome, you do image processing, no physics. It's physics. If you have a single spectrum, you can use photon counting to detect it. You can generate VMI. You can use one reconstruction into the material images. Then there is a method we call number one. We published the work in early time. Given the white images, each voxel should vary by local properties. If everyone is identical, it's piece of paper, nothing. So they must have some voxel variations. From this variation, Z is the major value. Equal, you can estimate two material under Z, each voxel, X plus Y. That's one equations. Z mean should equal to X mean plus Y mean. If you assume this variable is normal distributions. Now, problem is the second problem. Is many people have trouble in the static areas. Their paper review by TMI, 3 reviews are struggling from me. I saying, in which said, Jerome, you're young, you're energetic, let it go, let me go. I have 2 papers in TMI, let me go, young, energetic. Now, if Z equal X plus Y, many people I put the X, Y parameter. For example, X 20%, they put a 0.2. Y 80%, 0.I. That's people does work in static areas. We have trouble with that understanding. By physics Y, we cut the wax into 2 pieces. X has 1 pieces. X variable is variable. His portion Y is the probabilities. If X is 20%, Y must be 80%. You have 2 equations. Z you measured, equal X mean plus Y mean, unknown. 1 equal 20% X, Y% or 80% Y. You have 2 equations, you can solve 2 materials precisely done mathematically. So given those things, we can do single spectrum compute, see if we can do it. We get all kinds of VMIs. VMI is a critically important for me to understand. Maybe not that much. We don't know what to investigate. Maybe very critical, maybe not. But VMI, we did have real VMIs. Okay, I go very fast. We can use FBP plus all kinds of physics, machine learning to do FBP doesn't matter, over. Now we're going to do the basic reconstructions. For basic Y, like to bring you your A privileges is prime data. So we focus prime data to manipulate physics, deep learning, whatever put in. We cross, it's not important. The prior, they do spectrum photon counting. Here's the key, come to point. You have VMI for each energy from 1 keV to 120 keV, even higher if you use 120 kVp X-rays. We can generate wide spectrum you can imagine. Every VMI brings different contrast because tissue, water change contrast between energies. You have a contrast in 1 dimension, X, 1 dimensions. That's clear to you. Not contrast I give you physics, but does not give you biologies. So that physics why we improve results a little bit. You jump too fast. Go back. Then can I go back? No. Oh, I think I will go back a little bit. That's a key technology. General VMI is, everyone knows how to generate VMI. Someone different methods. Now we can do by single spectrum. You can use conventional CT. You can use photon counting. Doesn't matter. Once you get VMI, that's a key point. Each VMI reflects the contract for that energy as a physics.
Go forward.
Okay, let's go forward. Okay, maybe I'm too rushed because time is very little. I want to emphasize the key slides. Stop. Okay. Anyway, the physics bring VMI. VMI bring all contract for each energies. Now you have contract variation on energy directions. Now, next one is, can we do contract across the tissues on among each voxels? That's the key bring to the tissue biologists. What is best described so far we learned is tissue elasticities. Healthy tissue is very, very healthy quantities. Machine learning can know which one is best. Machine learning help us. Any degradation from elasticity is magnetic change. How we do elasticities? So now we compare to our physical science technologies. When you drive a car, time goes to zero. What you have? Speed. That's Newton tell us hundreds ago. When current vary on the image domain, people have done the work many years in the tissue registration, make it transform. If 2 points identified, you compute the transform to reach your tissue softness, right? That's the doing by tissue restrictions. What do we do? Same thing Newton teach us many years ago. When 2 points go to zero, what you have? Differentiation. So when we bring this differentiation to the relation transform, we have one requirement for transforms is invariant. In physics, any quantity has to be invariant. People in registration, they use 2 points to compare parameters. We said we don't. We just need to go to zero with differentiations. First order, second order. Can we use this differentiation to compute the elasticities? We did. We got it. The equation may not be precise, but reflect elasticities because it vibrate. Ultrasound, CT, MRI, let's say the ultrasound, MRI, and optics. They measure elasticities. They did something push. They vibrate the images, but they don't know. Newton tell us vibration-wise elasticities. If vibration goes to 1 point, the dynamic, that's differentiations. So Newton tell us 100 years ago, we got that one. When we have the two contrast, VMA and neighborhood elastic differentiation under the 2 points variation, when you go to zero differentiation, here we have results. Now talk about result is more careful. Bottom line is count the best long-larger differentiation. They bring all humans in the world. They bring all kinds of deep learning. They can AUC 89 to 88 to classify all long-largers. What do we do? We only have pathology largers. Each larger they have pathology. That's ground truth. If we use pathology, we have to do the two long largers. One is about 68 samples. One is about 114 samples. Results almost identical. Tell me why. The physics, the science speak itself. They should not depend on your sample data. Your sample data more or less will follow statistics. If the loss of the Gauss distribution more than 100 should be enough. They affect your deviations. For polyp, we have 3 categories. For large one, polyp is once in the final stage, you have to remove. We got 99%, 99.98%. We have two very strong baseline to compare. Type 2, type 4 are traditional machine learning. The handcraft features, LdCT features, upper dynamic features, wavelets, different features. We bring their four classical. They are very consistent. They got what? For large, you got about 60 something. That's exact match human's performance. Because they don't know what can do with the largest, they put the opposite. That's what they're doing. Their performance is around 70 to 50 random. So the conventional machine learning, they mimic a human's eye. Be careful, they mimic human's eye, just like do deep learning. Image-based, human-based image eye, that's numbers. Then goes to deep learning, we have 33 deep learning, 3D volume to the work. That's the best deep learning we can get from online. They got what they got about 70, still within humans' performances. Human, we call high load drive machine learning. So we mimic experts thinking. They look for image why they think of behind what's pathology behind. But their thinking why is not quantity, vary by vary. That's why human eye cannot do quantity. We model this by knowledge. Image. Image is one kind of surrogate of the tissue pathology behind. Remember, low contrast, low shape, low boundaries. I tell you, for med image, MRI, CT particularly, there's low borders. Every contrast. Contrast is very dynamic. Go back to yesterday, question, Chen Guangwen and people like, we don't like zero. We have so many dynamics to compute. No matter how large it is, you multiply zero, you get zero, or you lost information. This is a very, very tiny, you divide by zero, you can blow up infinity, so we don't like zero. So we try to avoid zero in all kind of computation. Contrast is dynamic. They have grading, they have change rate. So we have counter, we can compute this first order, second order. If you go high order Y, the loss come in. So the VMI is very minor. So first and second order is enough to get results. The one perfect. For polyp, 3D is looking for. For late stage, the polyp has been developed, it must remove no matter what. We got more than 99. That's pathology, win the games. The second one is large polyp. There's still the polyp, they have some kind of risk become malignant. They change the pathologies. We got what? We got the 97. Large, we got 98 because that's late stage. Large polyp still lower stage, we got 98. Large polyp have less than 1% become cancers. We got 98 already, 97. For small polyp, local body small polyp less than 1 centimeters. For GI doctor, I always say they remove all polyp with time, with manpower. For this very tiny polyp, we've got about 88 AUCs. This is the pathology winners in the science. If you got the image best, you're going to circle around. I circle 30 years, no way. My life is short, I will go this direction. This is winner. Thank you.